professors. I'm Shatin from Shatin College. Registration number is 60018. My research topic is the 3n+1 conjecture. The conjecture was first suggested by German mathematician Luther in 1950, so it's named after him. This conjecture concerns about this function defined here. The conjecture states that for all natural numbers, this process will converge to 1. And in my essay, I define this as a step. I omit all the even numbers as I believe them to be unimportant, and more that I call one or more steps as a path. My study concerns about these 3 directions. First, is there a path in which a number will increase without bound? If so, the conjecture is false. Second, why quality choose 3n+1 conjecture but not other coefficients? For example, why not 5n+3? Third, is there a cycle in a quality path? If so, we can also disprove the quality conjecture. To study my first direction, I concern about pre-numbers. Pre-numbers are back trace of a path, is some kind of inverse function. It helped me to construct paths which have special properties, and I use the properties to show that the limit of numbers of peaks in a path does not exist. Also, it helped me to find what kind of numbers will fall into the same path. Here are some results I get from pre-numbers. First, for odd number k, if it is a multiple of 3, then it has no pre-numbers. If an odd number k can be expressed in form of 3p+1, then it must have infinitely many pre-numbers in this form. Or if it is in the form of 3p+2, we can also find infinitely many pre-numbers in this form. And the second result is given any t number. T number in my essay, I define it as odd numbers which are not multiples of 3. For any t number k, we can construct a decreasing path of any length, and the endpoint is k. For example, if we want to construct a path with 6 steps to k, we can always construct such a decreasing path. Theorem 4 states that for any t number k and natural number r, we can construct a path to k of length 2r with exactly r peaks. That is, we can always construct a path that for every 2 steps there is exactly 1 peak. Actually, this theorem is not in its most generalized form. And theorem 6 states that numbers in this form and numbers in this form will always meet before 1. Actually, we can be sure that they will meet right after the first peak. We take log of the value and with the trend of the number of steps taken, and we can see that they will increase in approximately a geometric sequence series, and they will when they rise to the first peak, they will meet. Same phenomenon will appear for the numbers in these 2 forms. I believe that theorem 6 is the most important, because for any odd number, it can be expressed in either this form or this form. So that for any odd number, we can always find, without calculation, another number which is approximately half or double of that, such that the 2 numbers will always fall into the same path. And look at these 10 numbers. These 10 numbers meet at this number. I think it's very surprising and interesting. I believe that from this phenomenon, I believe that my theorem 6 can extend to in my theorem 6, I proved that some numbers in approximate ratio of 2 to 1 will follow the same path. However, conditionally, we are hopeful to extend it to a greater power of 2. And secondly, I consider why quality choose 3n+1. So I've studied a general form of his conjecture as defined here. The quality conjecture is the 3-1-2 conjecture. First, I proved that b must be equal to 1, for otherwise GB will always be a multiple of b and never reach 1. Looked at in my essay, I warned that b and c are relatively prime. And the case for a is equal to 1 is easy. The conjecture is true for c is greater than b, and is false for c is less than b. And I want that for every AR plus B, the numbers in form of AR plus B, they have a common factor C, so that the path is increase, decrease, increase, decrease, etc. So I found the common factor must be must be 1 or 2, so that the C for C is equal to 1 is impossible. So that for a conjecture to be possible, C must be equal to 2. And now we have solved all the cases except B is equal to 1 and C is equal to 2. When A is greater than 3, using expected value, we can see that the conjecture cannot be true for all natural numbers. So the 3n plus 1 conjecture is a reasonable guess. For others, we can easily know it is true or not. Now, we haven't considered that B may be negative, but the tricks are the same. Only the 3n minus 1 conjecture may be true for a negative B. However, this conjecture is not true. Consider this function for the 3n minus 1 conjecture. We find at least 2 cycles exist, so that we disprove this conjecture. However, I still believe this conjecture is important. Look at this cycle for the 3n minus 1 conjecture. In this cycle, 17 has been multiplied by 3 for 7 times and divided by 2 for 11 times in one cycle. In theorem 5, I state that if there exists a cycle for the 3n plus 1 function, there will be a corresponding pair of numbers in the form of 2 to the power m and 3 to the power n. The former should be a little bit bigger than the latter with very small difference in magnitude and in ratio. However, I find that the cycle corresponding to the one in the 3n minus 1 conjecture, the corresponding pair is here. The difference is bigger than I have expected. This shows that if the quadratic cycle exists, the difference between these two numbers may not be as small as I thought. I still believe that if we manage to find a solution for this equation, there will be one cycle for the quadratic conjecture. If so, the conjecture is not true. However, from the cycle for the 3n minus 1 conjecture, we should believe that even there is no solution set, the cycle may still exist. Although the 3n minus 1 conjecture is solved, I think we should still try to find as many cycles of it as we can. And we can generalize the properties to study whether the quadratic conjecture have some cycles which exist. I believe it helps us to know that. Here are some ideas I suggest if I am to further study this question. First, we should study the cycles for the 3n minus 1 conjecture. Second, we should use quaternary system. That is a number system in base 4, just like binary system is in base 2. Third, I think we can extend the theorem 6. In my study, I've tried several directions and they all indicate a little success. It's better than I've expected. I hope my investigation is useful and I could contribute a little to the advancement of this problem. Thank you.
Can I just comment